Welcome to ICSE Physics Class 10. In this video, we will be dealing with part B of the first chapter, which deals with the center of gravity. We will look at what the center of gravity is, and then we will have a look at what the balance point is. Finally, we will look at how to experimentally find the center of gravity for an irregular shape using the plumb line method. This video will be present on the Dayan Academy's YouTube channels. Links will be in the description as well as in the cards of this video. So let's find out what is the center of gravity. If we take any object and we zoom in far enough, we'll realize that these objects are made of many smaller particles. Each of these particles are acted upon by gravity individually. This means that every single one of these tiny particles actually has one such arrow drawn to them. However, all of these particles are connected and act as a single unit. And therefore, while calculating any numericals or figuring out what happens to this body, it would be much easier to assume that all of these particles are a single unit. And therefore, instead of having individual particles of weight W1, W2, W3, and so on, it would be much easier for us to assume that all of these different particles have a singular weight, which is the summation of all of the different weights acting at a specific single point. So therefore, the center of gravity would be that point where we can assume that the weight of the entire body is acting. However, we have to find out what would be the ideal place to assume this weight to be acting, which would be the center of gravity. So to find out what position would be the best, scientists have realized that it would make sense if we were to assume the center of gravity to be the point about which the total moment of forces is equal to zero. The summation of all the moments should be equal to zero. Why this is the case we'll look at while dealing with the balance point. Yet if we only state that the total moment of force should be zero, we actually miss out on a crucial point, and we'll have a look at that in this particular example. So imagine this torus shape. So this is a torus, that means it's like a donut in 3D space. This torus is also composed of individual points, each of which have a force in the downward direction. Remember that we can assume that all of them act perfectly downwards because we're assuming that these particles or these objects are much smaller than the Earth, and therefore they are in what's called a uniform gravitational field. This means that the force of gravity acts straight downwards, and it is acting perpendicular to the surface of the ground, parallelly. So in this situation, we can actually see that any point along this gray line would have a total torque equal to zero. Think about it. If we look at it from the top, there are approximately equal number of particles on this side as well as the other side. Similarly, there's equal number of particles on this side as well as this side. So the total torque or the total moment of forces about any point along this black line would lead to zero. So where should the center of gravity be placed? Because we can see that anywhere along this line seems to satisfy the condition that we deem necessary. And that is why it is very important to also state that the summation of torques has to be equal to zero. The summation of torques has to be equal to zero in all orientations or any orientation. Let's take a look at why that's the case. If we were to take this object and then rotate it in some arbitrary direction, we can now see that even though all of the arrows are still pointing downwards, if we were to take a point on this rod, the total torque about that point would no longer be zero. Because clearly in this sort of a situation, if we were to look at it from the top, there's much fewer particles on this side and there's a lot more on this side. That means that if we were to let this hang from a pivot right here, the entire object would rotate like this. Therefore, this point can no longer be the center of gravity. And that's why we have to take a look at such a position where no matter how we orient it, the total moment of force will always be zero. And for this torus that happens to be right here in the center, which also shows another property of the center of gravity, which is it does not necessarily have to be a part of the object. It could be in a place where there is no material at all. Hopefully that gave a good enough understanding of what exactly the center of gravity is. Let's take a look at a few examples of where the center of gravity is present for certain objects. I've marked the center of gravities with this green color sphere. So if we look at a rod, the center of gravity is present inside the rod in the center, and you wouldn't be able to see it unless you switched on X-ray vision. So it lies right there in the center. The same thing would happen in case of a plain circular ring. It would lie in the center, much like that of the torus. So it's easy to note that in case of any completely symmetrical object, we know that the center of gravity would lie perfectly in the center of the geometry. So with that, we can say that the center of gravity for a disk also lies right at the center of the disk. Similarly, when we have a sphere, the sphere could be a solid sphere or it could be a hollow sphere. Over here, we've represented a hollow sphere with a wireframe of the sphere, but imagine this is a continuous surface with nothing inside. So in both those cases, you would realize that the center of gravity lies in the exact center of the spheres. The same would happen in case of cylinders, where they would lie at a height of h/2. That means it's half the distance from the total height of the cylinder, and it would be present right at the center of the actual circle that forms the cylinder. Things, however, start changing when we take a look at cones. Because a cone is not symmetrical, that means the top clearly has lesser mass than the bottom. We actually see that in case of a solid cone, there's a lot of mass in the bottom, and therefore the center of gravity is pulled towards the bottom, and that's why it's present at a height of just h/4. That is assuming the height of the cone is h. However, in case of a hollow cone, the center of mass is present a bit higher because there's lesser mass at the bottom compared to a solid cone, and that's why it's present at h/3. Why this is h/4 and h/3 can actually be mathematically derived, and that falls outside your scope of the syllabus. But if you're interested, do let me know, and maybe we can have a lot of derivations for these types of shapes from outside your syllabus for those who are interested. Next, let's look at a triangular lamina. In case of a shape like this, a scalene triangle, what we'd have to do is find the medians and find the point of intersection of the medians, and that's what would be the center of gravity. To draw a median, you would have to take one side of the triangle and then bisect it into two equal parts. And then you would have to take the midpoint of that line, which is the area where you've bisected it, and join it to the opposite corner to form one line. And then you would also have to do the same for another side and the opposite and form a line. And the position where these two lines intersect is going to be the center of gravity. However, it's good practice to do it to the third side as well, just so that you can make sure that you have drawn it correctly and any errors can be fixed. But technically, 2 lines is sufficient to find the center of gravity for this 2D shape. Lastly, in case of any parallelogram, you would have to connect the 2 diagonals, and wherever the 2 diagonals intersect, that would be the center of gravity. Now, note that the center of gravity is basically at the same position of the center of masses as long as the objects are present in a uniform gravitational field. If the object is large enough such that the gravitational field cannot be considered uniform, the center of gravity would move away from the center of mass. With that, let's move on to what is the balance point. So the balance point is the point upon which objects can actually balance. For example, this meter scale is being balanced on a knife edge. The only way that that's possible is because the center of gravity of the meter scale lies right here. So the balance point is directly under the center of gravity, and that's over here. And because we're balancing it exactly on that point, the meter scale remains balanced, even on a knife edge. And if we successfully get the center of gravity perfectly, in that case, we don't even need a knife edge. In fact, we can use a single point. If we take a look right here, at a single point, we're able to balance this lamina simply because the center of gravity lies right here, and we're placing the pinpoint right under the center of gravity, which is the balance point. And now we can find out why this center of gravity actually required us to have the summation of moments equal to 0. That's because we wanted to assume that this entire object is a single point. If we were to assume that the weight of the body is acting, let's say, over here, and this is where the weight of the body is acting, in that case, when we place this body down on the knife edge, it would feel a torque. It would seem as though it should feel a torque, and therefore it would start to rotate and then fall down. Yet we clearly see that that does not happen. So the only way that cannot happen is if the center of gravity is in such a place such that the summation of torques is equal to 0. If this truly was a point object, clearly placing the point on top of the pin or the balance point would cause no torque. If we were to place the point object somewhere outside the knife edge, it would clearly fall down. And therefore, in order to find the center of gravity, we have to make sure that this torque is 0. So hopefully with that, you've understood what the balance point is, what the center of gravity is, and why the center of gravity requires the conditions of the total torque being 0 in any orientation, and what the center of gravity is for a few common shapes. And with that much, this portion, or at least the concept of this portion of this chapter, comes to an end. If you have any doubts or any queries, do leave them in the comment section, and we will make a video that deals with all of your queries. Until then, thanks for watching and all the best for your exams. Be sure to check out the Dhyan Academy video where we talk about how to find the center of gravity experimentally using a plumb line.